Okay, good morning. Is it audible? You can post in the comments if it is audible. Okay, good. Yeah. So you can, if you have any doubts, you can post in the comments. That is one thing. And if you want to ask any doubts, also you can just you know this WhatsApp number, my WhatsApp number. You can directly WhatsApp me. I will see the questions there. Okay. Okay. So then moving on. So in the last class, we have seen this. Okay, so last class we are looking into this um, discrete time Fourier transform. We have seen just the definition of discrete time Fourier transform, how it is defined. Okay, it's nothing but the projection of discrete time signal on complex continuous frequency complex exponentials. That means here two things we need to remember as soon as someone says discrete Fourier transform is the signal is discrete in time, but when you take Fourier transform it is continuous. Okay, that is the one point you need to, in frequency domain the spectrum is continuous. That is one point to note. The second one is since it is a discrete time frequency, so means like in time domain we have all the time axis as integers. So because we are expressing every signal in terms of sinusoids, and sinusoids are periodic with period 2 pi, so the maximum frequency component we can expect in frequency domain for any discrete time signal is pi radians per sample. Okay, so and likewise we have negative frequency scale also, like minus 0 to minus pi. So overall minus pi to pi is the fundamental frequency range of discrete time signal. Okay, so from that is h of omega or any x of omega, discrete time Fourier transform is periodic with period 2 pi. Okay, so and the next thing to note is as we have seen, like this existence of for discrete time for a transform. Okay, when a signal is absolutely summable, okay, that means uh, so if yeah, this one, if x of n mod x of n summation n is equal to minus infinity to infinity, uh, okay, this summation if it is less than infinity, then we say this is absolutely summable. For such signals, okay, we have DTFT convergence in uniform sense. That means uniform convergence. Uniform convergence means if you take only, instead of infinite samples, if you take only finite number of samples, like k n is equal to some minus k to k, like this, xk of e power j omega. So uh, this we call as DFT approximate for k, some order k. So this DFT approximate for order k will be equal to actual DTFT. Okay, sorry, DTFT approximate of order k will be equal to actual DTFT at each and every frequency as k tends to infinity. Okay, as k tends to infinity, at each and every frequency both will be same, so that this as k tends to infinity, the difference between these two will go to zero. Okay, this is when the signal is absolutely summable. Okay, if the signal, sometimes the signal may not be absolutely summable, but it has finite energy. Okay, that means absolutely square summable. That means here square will be less than infinity rather than actual x of n. So in such cases, for finite energy signals, we have uh, mean square convergence. So this is a square summability. That means summation n equal to infinity minus infinity infinity mod x of n square. Okay, this if this value is less than infinity, so for such signals we have this mean square convergence. That means uh, the actual DTFT value and the kth order approximation of DTFT uh, will not be equal at each and every frequency, but the error over a range of frequencies, okay, like minus pi to pi, overall error from minus pi to pi, square of this error will go to zero. Area under the square of that error will go to zero. Okay, so that means we have some positive regions and negative regions over this frequency range, and overall sum will be go to, it will go to zero as k tends to infinity. Okay, this is the second type of signal where the signal is not absolutely summable for this one by n. So this proof is there in Wikipedia. You can go through. So this is having some the proof is having little bit of other mathematic theorems involved in it. So if you are interested, you can go through into the. So we need to expand this in terms of, you need to uh, first take sin x Taylor series expansion, and then we need to do some, apply some other laws to get 1 by n square n equal 1 to infinity as pi square by 6. Okay, this proof is there in the Wikipedia. You can go through. Other, I will share the link later. Okay. So for such signals where they are absolutely not summable, but they have finite energy, for such signals we have the mean square error uh, of the actual DTFT and the kth order DTFT will go to zero. Okay, they have this mean square convergence. Okay, still you can define the DTFT for such signals also. Okay, there are and if the signal does not have finite energy also, like diverging signals, we don't have DTFT for such signals. Okay, so, and we have also seen what is Gibbs phenomena. Gibbs phenomena is nothing but when you try to approximate for example, yeah, which has sudden transitions in the frequency domain like this. Okay, so from exactly at omega c, there is a sudden jump from 1 to 0. In this case, the Fourier series, Fourier tool will not, okay, converge. Okay, they, at this point, there is a lot of uncertainty and sudden jump, discontinuity is there. The Fourier transform cannot approximate the discontinuities. Okay, instead what it will try to we are trying to approximate every each and every value of this h of omega or x of omega with the sinusoids. Okay, it will approximate this discontinuity also with sinusoid. So in such case what happens is you will get oscillations like this. Okay, and no matter whatever k you choose, this is order k, k 20, 30, 40, whatever k value you choose, these oscillations will not go down. And this effect is called Gibbs phenomena. Okay, wherever discontinuity is there, if you try to approximate that spectrum with sinusoids or complex exponentials, so whatever infinite number of sinusoids you take, okay, hk of e power j omega will never be equal to h of uh, actual dtft, uh, because of these oscillations. But mean square error will go to zero. Okay, between the h of omega and hk of e power j omega, the mean square error will be zero. So that comes under second category that we have seen, like which signals having finite energy but not absolutely summable. So now moving on to the new topics of DTFT. So by this time you should have some knowledge of solving or finding DTFT of any given signal. First you need to check whether the signal is absolutely summable or not. Second one is if it is not, then if it is absolutely summable, then you can directly put x of n in that summation, x of n e power minus j omega n, and you can mostly all the signals will have some geometric progression, some of geometric progression, geometric series kind of formulation. Then you can put we have seen alpha power n u of n kind of signals. Okay, so you can just use any infinite summation formula and put and you can find the DTFT. That is the basic way we can do. The second one is if the signal is not absolutely summable but it has a uh, finite energy. For such signals, you just put find kth order DFT. Instead of minus infinity infinity, you just put k. Okay, and later apply k, limit k tends to infinity. That will give you for finite energy signals, but not absolutely summable signals. So mostly we don't encounter such kind in our problems here. Okay, if you get, you should able to again solve it. Okay, and that is how we compute DTFT. So is it clear computing DTFT? If you have any doubts, can you just uh, sh- show me, okay, in the comment section. Okay, so then we move on to so there are different kinds of sequences. Okay, first we'll see this Dirac delta, or this is Dirac delta means it is in the frequency domain, delta of omega, and it follows the same definition of continuous time impulse signal. Okay, so what is continuous time impulse signal? Which has zero width and infinite height. Okay, the in the same way in frequency domain also, we sometimes have this impulses in frequency domain with zero, means they with zero width. Okay, delta of omega means it lies at omega is equal to 0 DC component, but height is infinity. Practically it is not impossible, but mathematical, for mathematical analysis we'll use this Dirac delta function in frequency domain. Okay, infinite height, zero width, and one more important thing is the area is unity. Okay, and I have, like we have already seen that any structure okay, which has a unit area, and the parameter is depending on the width. Okay, so for example, this you take rectangular pulse like this, whose width is total width is delta. Okay, minus delta by 2 to delta by 2 means total width is delta, and height is 1 by delta. What is the area of this triangle? Delta length into breadth. Okay, so if you treat 1 by delta as a length, so 1 by delta into breadth is delta, so 1 by delta into delta, it is 1. So the area of this is 1 second. Yeah, so so this area is 1. So this rectangular pulse can be considered for defining impulse. How you define impulse? Because this breadth is depending on delta, but is this breadth should be 0. Okay, breadth should be 0, height should go infinity. So for that, what we do is, if you take delta tending towards 0, limit delta tending towards 0, okay, and the area under this the rectangle is always 1. Okay, so then it will go to an impulse signal, impulse. Okay, that means as delta tends towards 0, this will become 0 width, and 1 by delta means 1 by 0, it will be infinity, height will go to infinity. So this is approximated as a delta function, this Dirac delta function, delta of omega. Okay, so in such way you can put a triangle or any other geometric, known mathematical geometric shapes that whose width and height are inversely proportional to with each other, and when you find the area of such a geometric structure, you should get 1. Okay, all such structures can be approximations to this delta of omega. So yeah, so this is one example. Find the DTFT of x of n is equal to e power j omega naught n. This is a sinusoid, okay, sing of particular given frequency omega naught. Omega naught is constant here, so you should not treat that this is function of omega. Omega naught is some constant like 0.1 pi, pi by 3, something like that. Okay, so if you want to find this DTFT, just substitute in the equation. Okay, and okay, just, yeah. So what is our x of j, x of omega is equal to summation n is equal to minus infinity to infinity x of n e power minus j omega n. So this is DDFT equation. So in the place of x of n, what we need to put? This e power j omega you need to put. Okay. So when you substitute that, what happens? So here x of need to take one paper. Okay, I will take here. So we have when you substitute here summation e power minus j omega naught n into e power, okay, this is plus j omega naught n given in this uh, so this is plus j omega naught n, so e power minus j omega n. So n is varying from minus infinity to infinity. I am not writing that. This is x of omega. So now this is nothing but e power j you can take common or yeah, minus j you can common it, and you can take omega minus omega naught n. Okay. This integral is actually difficult to calculate because it is varying from minus infinity to infinity. So what we do is we know this one thing called duality property. We'll use that. So delta of n, if it is having a DTFT, we already calculated delta of n. So it is 1. Okay. So when you take DTFT of 1, it will be 2 pi into delta of omega. So this is called duality property. This you might have heard in your signals and systems somewhere. Okay. So how you will get this one, uh, this duality property? So if you take the inverse DTFT of this, we'll go by this way, by inverse DTFT of this as, what is inverse DTFT of this 2 pi into delta of omega? So which is 1 by 2 pi integral minus pi to pi, so 2 pi into delta of omega e power minus j omega n, okay, d omega. And what is this value? So this is nothing but delta of omega into, where this will be, you can substitute in the place only at omega is equal to 0 it exists. So this will be same as delta of omega only, delta of omega into e power 0 which is 1. Okay. So okay, I think 2 pi is not there here, sorry. So 1 inverse Fourier transform is delta of omega. Okay. So so this is what is 2 pi should be there. Yeah, 2 pi should be there. Yeah. So this 2 pi will get cancelled, and minus pi to pi delta of omega d omega is always 1. So the dTft of delta of omega is 2 pi into delta of omega is 1. So which is this. Okay. So if you know this, we have this, then what we do is when you multiply e power j omega naught n to this, sorry, so j omega naught n is here, yeah. So what is the dt of t? So this we will get it as 2 pi into delta of omega minus omega naught. This is by frequency shifting property that we are going to see uh, in a while. Okay, as of now just feel that, okay, by using frequency shifting property we will get this. Okay, this you remember first. Okay, this I think, I hope you understood this. Okay, the inverse Fourier transform of 2 pi into delta of omega is 1. Okay, that means uh, x of n is okay, this comes under duality property also. We also see duality, what is duality property, okay, later. So this 2 pi k will be, anyway it is periodic with period 2 pi, so that's why this 2 pi k is there. So this 2 pi k, if it is not there also, it is fine. So it is same as this one only, because it is periodic with period, it has taken 2 pi k. Okay, so this delta of omega is an impulse function at omega. Okay, so yeah, at every, okay, this, since it is a periodic signal, if the okay, the if you have a uh, at omega is equal to 0, you have an impulse at omega is equal to 0. So it is periodic with period 2 pi. So that means at 2 pi also you have the impulse. Likewise, minus 2 pi also you will have the impulse. So likewise, it will go on from minus in omega, varying from minus infinity to infinity. So this is x of j omega plot. Okay, is it clear? Sorry, this is for this is located at this is okay, not, this is not exact plot. Yeah, since it is delta of omega minus omega naught, so somewhere here, so this is minus pi to pi, let us say somewhere here omega naught is there. So you have omega naught delta of omega minus omega naught will be here. Okay, likewise, this is minus pi to pi. So pi to 3 pi also you will have impulse here. Here also you have an impulse. So likewise, this is periodic. Okay. Yeah. So this is looking like a impulse train with equal spacing. Okay, so this will be pi minus pi plus omega naught, minus pi minus omega naught. So what could be this pi plus omega naught? Okay, like that. So this is a periodic impulse train with period 2 pi. The spacing between two impulses will be 2 pi. Okay, this has to be 2 pi plus omega naught. Yeah. So discrete time Fourier transform for that complex exponential you have seen. Okay. So if you uh, take, yeah, inverse DTFT of that. Okay, we have just proved in the other way, like if e power j omega naught n has this DTFT, what is the IDTFT of this one? So that if you take, so from minus pi to pi you substitute that DTFT equation, and here it's easy to show that okay, minus pi to pi you have only delta of omega. There are infinite number of impulses, but from minus pi to pi you have only one impulse, delta of omega minus omega naught into e power j omega and d omega. So here in the place of omega naught you will get in the place of omega, so what is its value? So this value is nothing but delta of omega minus omega naught into e power j omega naught n. This value is this. So this is a constant with respect to omega. It will come out of this integral. So this is the integral, minus pi to pi will be there, d omega will be there. So this will come out of this integral, and integral minus pi to pi, you have an impulse. The area under this impulse is 1. So 1 into e power j omega naught is e power j omega naught n. So that is the inverse Fourier transform of this. Okay. So this he has just written a general all the period, the entire spectrum he has taken, but from minus pi to pi you have only one delta of omega minus omega naught. Okay. So these are the most commonly used DTFT pairs. Okay. So as you said, delta of n has DTFT1 and one has DTFT of delta omega, but he has for entire, here he has written for omega varying from minus infinity to infinity. Okay, for all omega belongs to the range minus infinity to plus infinity. This is the equation. What is the equation for the omega varying from minus pi to pi only? Means only 2 pi into delta omega. So this value is equal to 2 pi is a constant, it will be there, and delta of omega, so where omega belongs to minus pi to pi. So from minus pi to pi only one impulse will be there. Okay, if you take minus infinity infinity you will have infinite number of impulses. Spacing is 2 pi. Okay, it is periodic with period 2 pi. Okay. So likewise, if you multiply this one with a complex exponential, these all impulses will shift by omega naught. That is the meaning of whatever problem we have seen. So that is called frequency shifting property. Okay, if you multiply a signal with a complex exponential with some frequency omega naught, so the spectrum will shift by that frequency omega naught. Okay, if this is x of omega, if you treat this as x of omega, this will be x of omega minus omega naught. The only difference is wherever omega is there we have kept omega minus omega naught. That means it has shifted by omega naught units. Okay, so that is the frequency shifting property. We will see that the frequency shifting of property of this DTFT in the properties. So so and the next one, unit step. Okay, so this is very important proper to find what is the DTFT of unit step signal. Okay, so unit step signal is neither absolutely summable nor absolutely square summable. Okay, so summation n is equal to 1 to infinity u of n is what, or mod u of n, whatever you take, it goes to infinity, because if you add infinite number of ones it will be infinity only. If you square that one also, still it will go to infinity. That means this is not a first case of the signal that is absolutely summable, or the second case neither it has finite energy. Okay, it is violating these two, but still you can approximate the DTFT does not exist practically, but the for third case signal, third kind of signals like this, which is neither absolutely summable nor have finite energy, you can allow this Dirac delta functions in the frequency domain, which practically does not exist, but still for mathematical understanding, some will have this kind of signals. Okay, for such signals, this will be the Fourier transform. So any signal will have a discrete time Fourier transform. For the first two cases, you can have absolute, I mean, it's practically meaningful DTFT. For the third kind of signal where energy is infinite and also absolutely not summable, you can have DTFT still, but you should allow impulses in the frequency domain. Okay, so how to prove this one? So we need to prove u of n. So what is the DTFT of this u of n? It is 1 by 1 plus e power minus j omega plus summation k is equal to minus infinity to infinity delta of omega minus 2 pi k plus 2 pi k, something like that, plus c has given. Okay, plus 2 pi k, plus or minus doesn't matter, since scaling is minus infinity to infinity, that means it has infinite impulses. So if you plot the spectrum, okay, 1 by 1 plus e power minus j omega will look somehow like this. Okay, from minus pi to pi, and there will be an impulse at omega is equal to 0. Okay, likewise the spectrum will have its periodic nature. All discrete time spectrum is periodic with period 2 pi. So sketch color, okay, that is the only supported sketch color as of now. I will just try for the next case. Okay. So this is the spectrum of what this. When you plot this, you will get something like this. Okay, this is at every omega is equal to 0, omega is equal to 2 pi, omega is equal to minus 2 pi. So you have these impulses. Okay. So this proof of this u of n, I'm leaving you as a homework. Okay, assignment. You just use this DTFT formula and try to find this uh, unit step DTFT. So text, I think it is visible. Okay, clarity is not so good now. Okay. So I think now it will be good. Yeah. Okay, now this we have already seen alpha power n u of n. Okay, for only alpha less than 1 it exists. For alpha greater than 1, the Fourier transform DTFT does not exist. Again, it will be neither summable nor absolutely summable nor absolutely integrable. So the u of n only is the special case because the power of u of n is half. You might have already known, okay, from your signal system what is the power of u of n. So when you apply this 1 by 2n plus 1 summation n equal minus n to n as n tends to infinity, so limit capital N tends to infinity, what is the power formula? 2n plus 1 summation n is equal to minus n to n. X square of n, so in the place of x square we should put u square of n. Okay, and its value is 1 when it is 1, when n is equal to 0 to n it is 1. So n is equal to 0 to n it is 1. So this will be there here. And what is it? N plus 1. How many ones are there here? N plus 1 ones are there. So n plus 1 by 2n plus 1. So limit n tends to infinity. So this is infinity by infinity form. You can just take two common one half common here. So uh, in the denominator, this is like the power will be, or you can take LH rule. You will get half. When you take LH rule, it is half. Okay. So that is the power of unit step signal. So power of unit step signal. So hope it is clear to you. So since we have finite power, so like it comes under partially like for finite power signal, and also there are few sinusoids for that also power is finite. So we also see in the next coming slides that cos omega naught n sin omega naught n, they are also not absolutely summable, and don't have finite energy. They are periodic signals. For all periodic signals, we will have this delta of omega component common, okay, in DTFT, that we will see in the next classes. So these are most important, this is the most important concept in DTFT. So the properties of DTFT, first thing is symmetry property, okay. So he has given any proofs? Not given. Yeah. So we'll take one by one, and we'll prove all the symmetry properties of DTFT. So this is the DTFT of x of n, and it is, since a complex quantity, it has the real part and the imaginary part. Okay. So let me show you. So x of omega. So I'm not writing e power j omega. I'm just writing omega means it is e power j omega only, just representing like this. So n is equal to minus infinity to infinity. So x of n e power minus j omega n. So what you can write this one as summation n is equal to minus infinity to infinity x of n e power j omega n. By Euler's identity, it will be cos of omega n plus, or since it is minus is there, minus j into, again I am taking summation because it is a linear operator, minus infinity to infinity x of n. I'm writing directly, okay, sine omega n. So this e power j omega n, I have written cos minus j sine. Again, this summation, this cos terms I am taking as one summation, and sine terms I am taking one summation. So this is also, n is a dummy variable here. Summation with respect to n will be, n will be nullified, and it is only function of, n is known, it is only function of omega. So and it is a real part, assuming that x of n is always real. So this is nothing but xr of omega, and this is xi, imaginary part, okay, including the sign minus will be there. So this is xi of omega. So plus j I am writing xr of omega plus j xi of omega is x of omega. So this value is this. So we are writing real part and imaginary part, and in imaginary part here negative will be there, that you don't forget. So this is uh, what we get, okay, x real and x imaginary. So if x of n is even function, what happens? If x of n is even, that means minus x of minus n. So this is the definition of even function. So if x of n is even, so you can write this as, when for all negative indices, the positive indices will be same. So this will be, you can write it as x of 0 will be there. So x of 0 cos 0 is 1 plus summation 2 into, okay, summation n is equal to 1 to infinity, this x of n cos omega n will be there. And this imaginary part will be 0. Why it is 0? X of minus n uh, is equal to minus x of minus n. So when n is equal to, since negative sign is there, so for all positive indices negative sign will be there. When n is negative, minus x of n will become, this means this will become positive x of, for example I am taking n is equal to 1. When n is equal to 1, this is x of 1 when n is equal to 1. Okay, when n is equal to minus 1, so this will be x of minus 1, which is minus x of 1. Okay, since negative sign is there here, because sign is okay, I think you know this rule. I'm just trying to do it mathematically. You know this rule. This is even function, cos is also even function. When you multiply two even functions, the overall result is also even function. So if negative indices are there, you can write 2 into 0 to infinity kind of thing. Okay, this is even function and this is odd function. When you multiply even function with respect to odd function, the overall will be, this is odd function. So overall will be an odd function. So when you add positive indices and negative indices, they will get cancelled with each other and the result will be 0. Anyway, at n is equal to 0, sin 0 is 0, so it will be 0. Okay, so what we left with, x of 0 is real, x of n is real, cos is real, so everything is real, so it is a real function of omega. Okay, so the result is real function of omega. So that's what he has given. Even is it clear? So if x of n is even, if x is even function, x are x real, this dtft is a uh, real, dtft is always real. The same way you can just find for odd signal, you can just find by yourself. Okay, now if x of n is odd, only imaginary term remains and real term will go to 0, and this will be purely imaginary. Okay, so that is the symmetry. Okay, even symmetry and odd symmetry. So if x of n is even symmetric, that means is an even function of n, the Fourier transform will be all purely real. Okay, there won't be any imaginary. That means phase is 0 for this one. There is no imaginary means phase is 0. Phase means phi of omega. If you represent phase as phi of omega, it will be 0. And for odd signals, phase will be pi by 2 always, because tan inverse imaginary part is non-zero, real part is 0. Tan inverse 1 by 0, tan inverse infinity. So phase will be pi by 2 always. Okay, for this odd signals. Okay, in general both have constant phase. Okay, so now one more important property here is uh, x of e power j omega is same as x star of e power minus j omega for real signals. Why? Because so what is x of j, x of omega? I am writing what he has given, x e power minus j omega. Okay, so omega r is equivalently, I am writing in the place of e power j omega, I am writing omega here for simplicity. Okay, this is summation x of n e power minus j omega n is DTFT equation. So if I take a conjugate on both sides, x star, so this is summation. Since it is a real signal, x star of n is x of n only, and this is conjugate of this one will be e power plus omega n. Okay, the conjugate applies for this whole thing, conjugate applies. So conjugate can go inside summation and it can be applicable to each and every term also when it is in multiplication. So x star of n is same as x of n, because x of n we are considering real, and e power minus j omega n is e power plus j omega n. Star conjugate of e power minus j omega n is e power plus j omega n. Okay, so how can you further write this? X of n e power minus j of minus omega into n, which will be plus j omega n. Okay, so when you compare these two equations, this and this, in the place of omega now you have minus omega. That means this is same as x of minus omega, which is x star of omega. So this is one real important property we need to have. So that means minus omega means here this is e power minus j omega. That's it. Wherever omega is there, you put minus omega. So that's what the property here is. X of omega is equal to x star of minus j omega. Or you can just put from here, what is x star of minus omega? Wherever omega is there, put minus omega. This will be equal to x of omega. Both are same. This equation, both are same. Now we have kept minus omega here, and here minus of minus omega, it will become plus omega. That's it. Same concept is represented in two different equations. Okay, so that is one. What is the meaning? This is called conjugate symmetry property. So conjugate symmetry. So what is the meaning of conjugate symmetry? Okay, so when you take magnitude of this, okay, I'll just clean this. So what we get, what we got is x star of minus omega as x of omega. So what is the magnitude of x star of minus omega? we can write this as magnitude of x star of minus omega into e power j angle of x star of minus omega in polar form. In the same way, this has to be equal to magnitude of x of omega into j angle of x of omega. If both are same and their polar forms will also be same, so from this magnitude and magnitude should be equal and phase should be equal. So from here what we can write is x star of minus omega magnitude should be equal to x magnitude of x of omega. Okay, and angle of x star of minus omega should be equal to angle of x of omega. These two should be same. So what is okay? What is magnitude of this x star of minus omega? So x star of omega we got it as okay. So for example, you have okay. So I am trying to bring in this direction. So so x star of omega, what we got? Okay, from this what we can write is x of what is x of minus omega magnitude, which is same as x star of omega magnitude. Okay, we can also write in in this way. So since we have seen two equations, both are same. So when you put minus omega here, this will become plus omega. So it is same like this. So from here, x star of omega is summation x of n power minus j omega n plus j omega n. Okay. So you can put it as x real part of omega plus j into x imaginary part of omega. So since the star is there, it will go star here also. So earlier we have seen xr of omega is nothing but you have cos term here, cos omega term we will have okay, x of n cos omega term. Here you have x of n sin omega term. Okay. So when you take x star of minus omega here, okay, So the magnitude won't change. That means cos minus omega is cos omega only, sine minus omega is minus sine omega. But when you are taking magnitude of this one, so still it is whole square. So magnitude means square root of real part plus square root of imaginary part square. So square root of x cos omega square plus x square root of x of n sine omega n square. Okay. So magnitude won't change. Okay, for if x of n is real. Okay, I will write more clearly. So x of omega is summation x of n cos omega n is the real part minus j into summation x of n sin omega n is the imaginary part. This is imaginary and this is real. So what is x of minus omega from here? Summation x of n cos minus omega n is cos omega n only, because cos is even function. This will become plus x of n sin omega n. Okay. So what is magnitude of x of omega? This is square root of xr square plus xi square. Omega I am not writing, just okay. And what is magnitude of x of minus omega? Square root of, still it xr is same, xi will become now minus xi here. Okay, so this is xr square plus minus xi whole square is xi square only. So magnitudes are same here. So this is nothing but the magnitude of x star of omega also, from the property just we have seen. Okay, this is same as this. Okay, so now what about the phase? Phase of x of omega is tan inverse of xi, imaginary part is xi by xr. Omega will be there, I am not writing that omega. And here what is the angle of x of minus omega from the second equation? This is tan inverse of minus xi divided by xr. So this minus will be there. So this is nothing but a minus tan inverse of xi by xr. And this is nothing but minus angle of x of omega. So from here, magnitude of x of omega and magnitude of x of minus omega is same. Okay, and but angle of x of minus omega is minus angle of x of omega. Okay, this is called conjugate symmetry. This happens when x of n is real. Okay, so all real signals will have their magnitude as symmetric. That means whatever positive frequency magnitude is there, negative frequency magnitude will also be same. But phase is odd function. That means whatever phase you have for negative frequencies, minus of that phase will be there for positive frequencies. Okay, you just note this point. Okay, is it clear till now? If you have anything, you can just comment. So I will just post a question in the Google form and put that in the WhatsApp. You just or I think I can put it in the comment section as well. Before going to the properties, let's okay. I will take at the end. Okay. So I'll just have a short break. Okay, you'll just stretch your feet and come back. We'll just continue after this. So please answer the attendance question given in the comment section. Okay, welcome back. So the so whatever I have told you, I just want to give a hint on finding the DTFT of U of n. So what you do is try to find we know the DTFT of this signal a power n U of n. Okay, this limit when you apply a tends to 1, this will become U of n. Okay, now you consider this whole thing as a signal and take the limit outside and try to find the Fourier transform of this one. Okay, and except at a is equal to 1, okay, for all other a, okay, so this will be going to uh, is like as in the solution we have 1 by 1 minus a into e power minus j omega. For this, if you don't have limit a tends to 1, for this you can directly find. Okay, but when a tending towards 1, then you will get some other factor in 0 by 0 form. From that you need to actually, that is the hint. Okay, the hint is this is the hint to solve this Fourier transform of u of n. You represent u of n as a power n u of n and limit a tending to 1. Okay, and carefully you need to see the mathematics. Okay, though if you are able to do this, okay, you are good at mathematics. Okay, so then we'll see the properties one by one. Okay, so here we represent a signal as small letters in time domain and capital letters in frequency domain. N is the time variable and omega is the frequency variable. In generally, we'll write e power j omega, okay, in the parenthesis as argument. Okay, so h of n is another g of n is one signal which has g of j omega as Fourier transform. Let h of n is another signal whose Fourier DTFT is h of e power j omega. Okay, so the linearity property. The first property is the linearity property where alpha. So when you combine these two signals linearly means weighted sum. Okay, weighted sum of these two signals. Their spectra also get weighted summation. Okay, the spectra also combined linearly. Okay, what is this proof is very easy. So we need to find Fourier transform of linear combination of two signals alpha into g of n plus some beta into alpha and beta are some real numbers. Okay, we won't take complex for linear combination in general. So g of n into h of n. What is the DTFT of this one? So that means it is just summation n is minus infinity to infinity e power minus j omega n. This is the DTFT equation. So this alpha is a constant. It comes out of this summation, not depending on n. So this is alpha into g of n. This e power j omega n you can take here. This is just multiplication of two numbers, one real and complex number, plus, and beta is also independent of n, so it will come out, and another summation h of n e power minus j omega n. So what is this one? G of omega, and this one is h of omega. So beta into h of omega. So linear combination of the time domain signals, two different time domain discrete time signals, also lead to the linear combination of their corresponding DTFTs. That is the linearity property. So we'll see the attendance at the end. Those who have not submitted the attendance, I will just at the end I will tell you. Okay. So hope this linearity property is clear to you all. And the second one is the time reversal property. Okay, the proof is, I think you need to do all these proofs by yourself basically, but I'm just quickly doing this. Okay, g of minus n, just to substitute n is equal to in this equation, n equal to minus infinity to infinity e power minus j omega n. Okay, this is the Fourier transform of g of minus n. So now put p equal to minus n. What happens? P is equal to, anyway these limits won't change because the sum of n terms. If you add a plus b plus a is same as, okay, commutative property it will accept. Okay, so this is like g of p in the place of what I can write it as e power minus j into, it should be e power plus j omega p now in the place of minus n or so what I will write is, I will assign minus to this. Okay, this is p. Okay, in the place of plus p I am writing minus into minus. Okay, that's it. So don't keep any messages related to attendance, so we'll see at the end. Okay, so this is this is nothing but Fourier transform of g of n or p. Again you can replace p with small n, and this is looking like that, but in the place of omega you have minus omega, so this will be g of minus omega. So in the place of so what is the DTFT of g of minus n? We got g of minus omega. As I said, minus omega is same as e power minus j omega. That is just a notational difference. So next, third one is the time shifting property. Okay, so this also very simple. Now substitute what is the DTFT of g of n minus n naught. So summation n varying from minus infinity to infinity e power minus j omega n. So now in the place of n minus n naught, you put p. Since the limits are from minus infinity to infinity, so this whenever when you change the, when you add some little bit, so that means from here n is what, p plus n naught. So when you add some, n naught is some integer, some small integer value. So when you add integer to infinite values, you won't get much effect in this summation, since still it is minus infinity infinity only. So this will be g of p e power minus j omega. In the place of n, it is p plus n naught. How will you write this one? Into two terms, e power minus j omega p into e power minus j omega n naught. Okay. So what is summation over p e power minus j omega p? So until this is independent of n now. So this is g of omega. So this will give rise to g of omega into e power minus j omega n naught. So that means what is the meaning of this one is when you delay the input signal by n naught, then its dtft will get multiplied with this is some phase term. There is no magnitude here. Magnitude is 1 for this e power j omega n naught. Magnitude is 1 here only when you take single term, this single term. So this is some phase term. So some phase term will get multiply with this one. So this is the delay. So the delay, okay, this is the delay. It corresponds to what? Phase shift. Okay. So this the modify or in general phase will get modified. Phase will get modified by this factor, which depends on delay, entirely depends on delay n naught. Okay, n naught is the one which is important in this phase term. Omega anyway is a frequency varying from minus pi to pi. So when you delay a signal, it affects the phase of the spectrum. Okay, is it clear this one? Yeah. So now the next property is frequency shifting. This is just what we are talking about in this multiplying with j omega n naught. So frequency shifting means when you multiply a signal with a complex periodic signal. Uh, so this omega naught is some constant now. Omega naught is just like as it or pi by 3, pi by 6 something. Okay, what is the dtft of this one? So this is the signal, this is some other signal, this is complex signal now. When you multiply these two signals, what happens? So what is the dtft? Dtft means take summation and multiply with e power minus j omega n. Okay, so these two complex exponentials now we combine. This will become e power j minus j into omega minus omega naught into n. So this is a g of n summation over n. So what is this? This how is this look like? This is g of n into e power minus j omega n. In the place of omega, now we have omega minus omega naught. So this is nothing but capital G of omega minus omega naught. So what is shifting? Omega is shifting here. From earlier, when you take g of n alone, so for g of n, you have a dtft of g of omega. When you multiply this with some e power j omega naught n, another signal which is purely is a complex signal. When you multiply a complex exponential signal with a fixed frequency omega naught, this will shift to okay g of omega minus omega naught. The spectrum will get a shift. Okay, so this is called frequency shifting. Frequency variable is shifting when you multiply a complex signal in the time domain with the actual signal. Okay, so this is one way. It is basis for your modulation. What is modulation or frequency? That means when you have a signal, when you multiply with some carrier, okay, your spectrum will get shifted to that carrier. So this you consider it as a carrier signal with frequency omega naught. Okay, so earlier g of omega is here at omega is equal to 0. It is a baseband signal. Okay, when you multiply or after modulation, what happens? Okay, this is 0 and this is somewhere here omega naught will be there. So it shift from 0 to omega naught. Okay, so this is frequency shifting or modulation property you can call. Okay, only thing is we are taking it as a, uh, complex signal. Okay, so next one is differentiation in frequency property. Okay, so unlike the properties which we have proved in by taking direct DFTs, now we take this property, we take from prove from IDFT equation. Okay, so that means we have IDFT equation as g of n as 1 by 2 pi integral minus pi to pi g of omega e power minus j omega n d omega. Okay, not this one. Okay, we'll take another one. So okay, we'll take DFT equation only directly. G of omega is equal to summation over n g of n. This is DTFT equation, sorry. E power, this is plus j omega n, this is minus j omega n. So now when you differentiate this with respect to omega, so what happens here? These are all independent of omega. Only this one is independent of omega. So this will get uh, multiplied with minus jn. Okay, so now you can send this minus j that side, 1 by minus j dou by, this is partial differentiation. Okay, we are differentiating only with respect to omega. This will be equal to summation over n into g of n. I am combining e power minus j omega n will be like that only. So what is this? This is nothing but DTFT of n into g of n. Okay, what is the DTFT of n into g of n? This one. So this is like new DTFT 1 by minus 1 by. So this minus 1 by j, you can write it as j. J into dou g of omega by g omega is the DTFT of n into g of n. Okay, is it clear? Yeah. So this one is okay. So that is differentiation in frequency. Okay, and differentiating in frequency. Okay. So now this one important property is the convolution property. So convolution. So when you convolve two signals in time, this you might have already know, in frequency domain they get multiplied. Okay. So for this we'll take direct this convolution is defined as summation over k g of k h of n minus k. K is varying from minus infinity to infinity. I'm not putting the limits unless it is specified. The limits means it is minus infinity. I'm not giving any limits means it is minus infinity to infinity. Okay. So in the place of g of n convolved, so this is g of n convolved h of n e power minus j omega n is the DTFT of the convoluted result. Okay, this is some y of n or whatever it is. Okay, so here I am substituting this summation over k g of k h of n minus k. In the place of convolution, I am putting the convolution formula. Okay, so now you take this summation over k outside and g of k outside, and what you take is inside n, h is function of n, so h of n minus k you take, and e power minus j omega n you take. What is this one? Is this the property that we have seen recently as the time shifting property? In the place of n naught we have k here, so this will give to the actual DTFT multiplied by this phase factor. So this is so from time shifting property, so this you can write it as h of omega into e power minus j omega k. So e power minus j omega naught n into this one. So this is the dt. This is of the form DTFT of this one. So this is you can write like this, and the summation k g of k will be here. So this equal to h of omega is independent of k. So h of omega I am taking out. And what is g of k e power minus j omega k summation k, which is nothing but g of omega only. So this is like DTFT of g of k. It k is varying from minus infinity. That is g of omega. In the place of n, you have just k. Okay. So when you convolve two signals, okay, the DTFT, okay, DTFT of convolution is multiplication. Okay, convolution in time results to multiplication in frequency. So convolution in time, multiplication in frequency. Okay, that is this property. So now the modulation property, this I am leaving you as leaving it as homework to you. So you just do it by yourself. You need to actually here you need to um, what we call come from inverse DTFT to DTFT. Okay. So how I define, for example, g of omega convolved with. I'm just giving the hint, and you just do by yourself. So this is nothing but 1 by 2 pi integral over minus pi to pi. Convolution should be in this range, in this frequency only. Okay, so 1 by 2 pi we are writing because we are getting 1 by d omega here. So if it is df, this 1 by 2 pi won't be there. Okay, so whenever it is d omega, you need to write 1 by 2 pi. Okay, so and this is like a continuous time convolution, but in frequency domain now the variable is different. Now the frequency is variable. Here this is g of tau into h of t minus tau. So in the place of t we have omega, so omega minus tau d tau. So yeah, this is d tau. So tau is also in radians per sample unit. So same unit. You are subtracting means these two have same unit. So that's why you can put 2 by here. So like in just if tau we actually use for measuring time. So that's why what we do is we'll put theta g of theta in the place of tau. So now in the place of g theta, g of theta, you substitute summation g of n e power minus j. What you need to substitute? What you need to substitute here? Theta, because here it is frequency variable is omega, so here you need to put theta. So substitute this here, okay, and rearrange the terms, okay, and you just take n terms aside and theta terms and just try to use this as frequency shifting, use the frequency shifting property and get inverse dtft of h of omega minus theta as h of n into e power j theta n. So like that you will just do, you finally you will get as g of n into h of n. Not no, okay, so okay, this is sorry, this is the convolution only I have written. So you need to take idft of this one. So you take idft of this one, substitute in the idft equation and just uh, substitute in the place of g of theta its Fourier transform and you compute. Okay, in this way if you proceed you will get. Okay, otherwise you might have to do lot of computations. That is modulation property, and Parseval's theorem is very easy again once again. So yeah, so from this modulation property only you can just extend this. Okay, two signals multiplied here, also two signals multiplied, and taking summation n is equal to minus infinity infinity. Okay, so yeah, actually we'll do this in the next class by defining correlation also, so that we'll get some more intuition of what is energy spectral intensity. Okay, so this we'll do in the next class. Okay, we'll stop at this point, and in the next class we'll see an example problem for each and every, okay, property, and we'll define this and we'll see some examples. Okay, if you have any doubts you just post in the Piazza or WhatsApp. Okay. Thank you everyone. So I have activated uh,
I'm giving just 1 minute time. Whoever wants to, whoever are left, just activate it.